Okay, today we're covering chapter 17 quickly. Some of these concepts might be or might have been useful when looking at the data, but also just these are topics that are going to come up in future courses, so it's important to cover them even if we don't do any extensive technical exercises. So here we go. Let me close some stuff here. Okay, so this shouldn't take too long to get through 17. I'm not going to go through the examples in Excel. I really am more concerned about the concepts for this course, and then we'll move on to talking about any questions you might have about past homework or your final projects. All right, so chapter 17 is all about classification and clustering. And in order to understand that, we need to talk about data mining and what that means, because we can't do classification or clustering unless we have a large volume of data to do it on. So data mining attempts to discover patterns, trends, relationships among data, especially things that aren't obvious. And when we have a large volume of data, it gets harder and harder to find these patterns and trends. So we start with a data warehouse. And we construct data warehouses in a very special manner so that we can study these patterns in the data efficiently. This is not the same as a database that a company might use for like its day-to-day operations, where they might like store employee information and access or something. Data warehouses combine data from multiple sources. It's structured data. It's already been cleaned, transformed, and loaded, and it allows us to quickly and accurately respond to queries. A scaled down version of a data warehouse is called a data mart, and it might be like a part of a warehouse or a mini warehouse, and it would be generally for like a specific department of an organization. So like the sales department might have a data mart with sales data. So once we have a data warehouse, we can mine data within it, and there's several things we can do. We can do classification. So this is finding variables related to usually a binary but categorical variable. Prediction, we talked about prediction early on. Cluster analysis, so trying to group observations into clusters so that we can figure out which data is like other data and make observations about how those clusters are and aren't alike. Market basket analysis is trying to find products that customers purchase together. So if you're on, for example, if you're on Netflix and you watch a movie, it might try to recommend similar movies, or if it'll look at all the people who've watched that movie and see what other movies they're watching to make better recommendations. So, and a lot of online stores are the same thing. So Amazon, for example, says, I see that you purchased this. Here's what other people are buying when they buy this, to try and increase visibility of other products and get you to bundle products together that you might not have bought otherwise. And then forecasting, which we talked about a few weeks ago. So predicting values of time series variables. There's lots of software packages out there to do this. Most of this is really truly beyond the scope of Excel, even though they have some Excel examples. They're mostly for your understanding of the concepts. We wouldn't, at this point in this stage, when we're talking about classification and clustering algorithms, we would no longer use Excel. We would move on to more advanced software. So classification is a very common problem when we talk about data mining. It's basically regression analysis, but with where our dependent variable is categorical, and but it's the same objective. So we want to use data from explanatory variables to classify each record into a known category. We use data partitioning to do this. So before we apply an algorithm, we have to divide up our data into 2 or 3 sets. Usually at a minimum, training and validation, which is often 70-30. So 70% of our records would become the training set, and then we would train our algorithm on that data. Then we would run the other 30% in the validation data through the algorithm to see how well it performs with that data. This is to make sure we didn't under or overfit our model to the training data. So the testing set or the validation set would do that. Some packages also let you divide into a third set of data called a prediction set, where you don't know the values of the dependent variable, and the model will classify them, but that's less common. So logistic regression is a popular way for classifying individuals if we have the values of a set of explanatory variables. So it's basically using probability to determine whether or not an individual is in a particular category, and it uses a nonlinear function to do this. So it's regression, but with a binary dependent variable. So the variable is either 0 or 1, and then at some point it flips to 1, meaning so it's not likely to be in that class, and then after a certain point it is. And for these types of problems, that binary variable is going to tell us whether that observation is in category 0 or category 1. We use a nonlinear function for this. It looks, the probability is shown below, but we don't need to get too much into this math. The point is that we can manipulate algebraically that equation to get an equivalent form. And this is just telling us that the natural log of the probability divided by 1 minus the probability is a linear function of the explanatory variables. And then that ratio of p to 1 minus p is the odds ratio. So the logarithm of the odds ratio is called the log odds. And basically the whole point of logistic regression is to state that the log odds are a linear function of the explanatory variables. The goal of logistic regression is to interpret the regression coefficients correctly. So if a coefficient b is positive, then if its x increases, the log odds increase, so the probability of it being in category 1 increases. And then the opposite is true for a negative b. So just by looking at the signs and the coefficients, you can see which x's are positively correlated with being in category 1 and which ones are positively correlated with being in group 0. In a lot of situations, the primary objective of logistic regression is to just score the members given their x values. So however many x explanatory variables you have, you just want to score your members. So the ones who score the highest end up in 1, the ones who score the lowest end up more likely to be in 0. And there's some point in the middle where you're flipping between 0 and 1, that's not so good, and those are where you get most of your errors in classification. And then, so another way to do this is to have like a cutoff probability. So if they score below that cutoff, then they become 0s. If they score above it, they become 1s. So in the book, they walk through what this looks like, classifying lasagna triers. And if you want to walk through this example in the book, you can. They use stat tools, but the whole point is they're trying to figure out if they have or have not tried the frozen lasagna product. And then so they run the regression using stat tools, and when they do that on this data, they get the following results. So if the probability is greater than 50%, then they classify that person as has tried. If it's less than 50%, hasn't tried. And then this is the classification matrix. So it spits out the has tried, hasn't tried, and then the percent that it guessed correctly. It also gives you a list of all the original data and your scores, so you can see where it was incorrect. So in so explanatory variables for new people, those people whose status isn't known, can be fed now into this equation, and then they would be scored based on the equation. This will tell you who's most likely to have tried or have not tried, but from there it would be up to you to figure out what to do with that information going forward. So StatTools also does another technique called discriminant analysis. It's a pretty old technique. It's similar to logistic regression, same objective, but you won't hear about discriminant analysis much anymore. You generally will hear people using logistic regression. So, but if you hear that term, just know that it's just a different way of doing logistic regression. Neural networks are fun. These attempt to model the complex behavior of the human brain. So they send inputs through a complex nonlinear network and it produces one or more outputs. These are used to predict categorical dependent variables or numeric dependent variables. They're generally very accurate. However, the equations are not easy to interpret. So each neural net has an associated network diagram, and this is a very simple one. In real life, these network diagrams are very complex, which makes them harder to interpret. But you have these inputs that go through a series of calculations and then come up with an output. And in this case, we have 2 inputs and 1 output, but there's this hidden layer with hidden nodes. And scale values of the inputs enter the network on the left side. They're weighted by these W values and summed. The sums are sent to the hidden nodes, which they're then squished by some logistic type function. And then those are weighted and summed, and then the sum is sent to the output node where it's once again transformed and then rescaled. So much more complicated. These neural nets are trained by sending many sets of inputs, even the same one multiple times through the network, and then comparing the outputs from the net with the known output values. So the learning style for these is a little bit different. And StatTools doesn't do neural nets, but there is a neural tools add-in. No need for you guys to go mess around with that. But if you're curious about it, you can walk through the example in the book and just see what it does. So they create their training and their test data and prediction data, and then they have their dependent and independent variables. And then to train the data, the tool will activate the data sheet and it will run through the algorithm, and then it will spit out the results. And this process with the same data ends up being a little bit better than the logistic regression. So 18% of the classifications in the logistic were incorrect, and on this one, I think it's like slightly less. It's like 10 and 6 or so. Okay, so in the book they go through that example. You'll also hear a lot about Bayesian algorithms and naive. These are simple classification methods that are very different from logistic regression and neural nets. They're common for text mining. The basic idea is to find the conditional probabilities of given sets of the explanatory X values, given that the dependent variable is 0 or that it is 1. So probabilities are calculated from the observed training data for all observed sets of X values, and then for a new observation, they would look up the probabilities for those explanatory X values. We can use Excel, but not in a very good way. We wouldn't do this in practice, but you can see through the example, if it interests you, how they bin the training data and then calculate the probability of X given 0 or given 1. And then each of these is a product of probability, so they're usually very small. Then the algorithm uses the natural logs of the individual probabilities and the fact that the log of a product is the sum of the logs to come up with its classifications. So this is kind of what the output looks like. We can also do classification trees or decision trees. So this is the type of work that I was talking about doing for West Point Academy to choose a new ITSM system. They we are using what's basically called analytical hierarchy process, which is using decision trees to weight inputs and then calculate a recommendation, which is the output. So this is a relatively intuitive method that can discover nonlinear relationships. None of the software in the book would cover this. In fact, my company uses a very highly specialized software to do it. You could build these out by hand, but that's very intensive. And if you have more than a handful of objectives to weight and more than a handful of alternatives to score, it's really gets very complex very quickly. So yeah, generally you would use software for this. And the idea is that you split a box of observations into 2 or more boxes, and you just keep doing that to make these boxes, these variables, more and more pure. So each box is more nearly yes or no, yes then no, or vice versa. So you're getting closer and closer to definitely yes or definitely no. And once you get to a certain threshold that you set, then you stop splitting. And then your final result is this set of rules for classification, and they're very simple. So that type of tree might look like this. So each box has a bar that shows the purity of the corresponding box, where black corresponds to yes and gray is no. Actually, and then this, I believe it's actually, looks like blue and orange. So blue is yes and no is orange. So we split everybody into mall trips less than 4, mall trips between 4 and 6, and mall trips between 4 and 5, because it's less than 6 and it's not inclusive, and then mall trips greater than or equal to 6. So now you can see that mall trips less than 4 is looking pretty heavily yes, but still not great. So then we would split that into some more factors like west or not west, not east and east, and then by age. And by the time, and we split mall trips down here by age. So if we're looking at mall trips greater than or equal to 6, and we look at how many of those people are greater than or equal to 42 or less than 42, you can see by the time you get to this rule right here, they're nearly all yeses. So you can stop trying to split out this data set to develop rules. When we do classification, whichever method we choose, we're trying to establish whether or not our algorithm is accurate. So we'll be looking at precision, specificity, and sensitivity. So precision is, of all the rows that I predicted to be yes, how many were yes? Truly. Specificity, or the true negative rate, is of all the testing rows where the dependent variable is no, how many were correctly classified as no? And then sensitivity is the true positive. So of all the testing rows where the dependent variable was yes, how many of them were correctly classified as yes? This is graphed with an ROC curve, and it provides a basis for choosing a good sort of cutoff value. So we have the false positive rate and the true positive rate graphed here. And then lift measures the increase in the number of purchasers reached by choosing one technique over just a random approach. So that blue line is, I don't have any model at all. The ideal model would be in red, and then our classifier is that line in green. So the lift is the difference between no model and our model. We also often use classification for data sets that have rare events. So we want a lot of packages accompany predictions of new observations with the probability that that prediction is correct. So we can sort on the probability of our predictions to see which ones are the least likely to be correct. And then if we're forced to choose some observations, we can choose the ones with the lowest probabilities of being classified as no. Just a way of sorting out the data to look for those rare events. Okay, so classification and clustering. So classification is generally supervised. So we have a dependent variable we're trying to predict, and all of the methods that we talked about would generally be supervised. You can do unsupervised classification, and if you watch the video that I interviewed Todd Lindgren, then you would, we talk a little bit about that as well, but generally classification is supervised. If we're doing unsupervised data mining, we don't have a dependent variable. We're just looking for patterns or structures in the data. So this tends to be clustering. This would be like the market basket analysis example that we talked about earlier. Clustering is the most common unsupervised learning method. There's other like text mining methods that are unsupervised as well, but the book covers a lot of these that they refer to as segmentation. So we're trying to group entities, either customers, cities, something into to some unknown number of clusters based on the values of their variables. We don't have fixed groups like the tried and hasn't tried classification with the lasagna example. We're just trying to discover how many groups there might even be and what are their characteristics just based on the data. The key to this is development of a dissimilarity measure. So once we have that developed, the algorithm tries to find clusters of rows so that the rows within a cluster are similar and the rows in different clusters are dissimilar. And once it's figured that out, then we have to explore the distributions of variables in different clusters to figure out what those clusters are and to name them. So a very, very popular clustering algorithm is k-means clustering, and k refers to the number of clusters. So the book uses this tool called Evolutionary Solver to find 4 cities to be used as cluster centers, and then it assigns all the other cities to one of those centers. So we're setting k to 4, and then there's 49 cities. So in typical k-means clustering, the cluster centers aren't necessarily equal to an existing number, but in this case, we've set it up that way, but the idea is still the same. So all that's saying is that in true k-means clustering, the cluster center doesn't have to be a member of the data set. So the example runs through how to do that and looks at all the data from these cities. And there's a point here, if you use raw units in this example, they drive everything because those values are more spread out than other demographics. So to remedy that, they standardize the demographic attributes. So just the whole point of that should just be that sometimes when you're doing these algorithms, you need to perform operations on your data to standardize it or clean it or normalize it in order to get better results. So anyway, it walks through a whole thing, and then it ends up assigning all of these cities to cluster centers, and they're assigned based on the smallest distance. So the whole point of the k-means clustering algorithm is to calculate minimum distances from each point to its cluster center. So it's figuring out where those centers are so that all those distances are minimized in total. Then you get this solution. So it comes up with these 4 centers and then the cities associated with them. There's another example where they do this with shoes, but really, again, for this week, the whole point is to kind of introduce you guys to the idea of classification and clustering. There are other courses that go into these concepts in greater detail. but for the purposes of this class, because we wouldn't really use Excel, that's why I saved that for week 10. Just, I want you to be aware of those things. They may have helped you with discussing the results of your data, but again, we would not be really playing around with that kind of stuff in Excel. So I'd rather not assign you problems from these. I'd rather be working on your final project. So that's why we saved that for the end. Okay, so as promised, the rest of the time for us now is just dedicated to helping you guys with any homework that you need to catch up on or the final project. So let me